Okay, I think we'll get started, and welcome to the fourth and last lab in the Machine Learning for General Chemistry Part 1 experience. And we're going to continue with our image recognition we talked about last time, and this includes using the convolutional neural network approach. So again, a lot of the key ideas relative to the last lab. So supervised learning, we're going to give the system a image and some metadata that describes that image, and so it will know the result, or it will know what that image stands for, and so then it can learn via that supervised style. And then we will give it a new image, and it will be able to then make some predictions. And so we're going to plot those predictions, plot the expected versus, or the predicted versus actual, and the residual plots. The application here is going to be to mimic a case where we're interested in surface reactivity. So we're going to have the surface, and it will have some defects, and we'll look at the reactivity of that surface. I talked about this last time, but I'll just recap the idea of a convolutional neural network. So this is a very common machine learning algorithm for identifying features in images. And so what a convolution is in this case, we take a mask or a filter that goes over the image, and that filter is looking for a specific feature. So it might have a slit in it, a horizontal slit. And so if we have a square object, as we convolve or pass that filter through the picture, it will give a high signal or a high match when that filter crosses the horizontal, or the top and bottom lines of that square. In each, we then might have a number of filters that would look for different shapes, maybe a vertical line or a line like this. And each of those occur at a given layer in this convolutional network. So we have the input layer where the images come in, and then we have a bunch of hidden layers. The number of layers here, the fact that there's more than one layer classifies this as a deep neural network. So you hear about deep learning. It's referring to the number of layers there. And we are, in this lab, we're going to look at a 2-layer model, 3-layer model, and a 4-layer model. And then we have this output layer. And so these adjust, these different nodes in this network adjust according to weight values based on the training set. And then when it sees a brand new image, it's able to match that with what it has learned from the previous images. All right, so I kind of mentioned this before, but the application here is I've made a square lattice and then randomly remove atoms in that square lattice, and that leaves edge atoms, atoms that are not completely connected to other atoms. And these are usually sites of higher energy in the surface or on the surface, and can be more reactive. So it's not unrealistic to think that the surface reactivity of these crystals will be proportional to the number of edge atoms, and so that's what we're going to take here. We're going to randomly pull out atoms from 100% pristine crystal all the way down to 50% defective, and we will calculate the number of edge atoms and then show the crystallographic image, or the two-dimensional Fourier-transform of that surface. So what an actual crystallographic instrument would be looking at. So we're just going to look at the raw image coming from that instrument. We won't train it on the lattice itself, but on the actual data that would come into an instrument. It will know where that came from, and by learning to look at the crystallographic data, it will be able to then correlate how reactive that surface is based on the number of defects that change the look of that crystallographic data. And so we'll be able to predict surface reactivity. So let's go ahead and get over to the computer and go through this lab. Now, before I do that, I guess I should say this lab is actually pretty computationally intensive. So unlike the last lab where the data sets, the the learning algorithms were already pre-trained. Part of this lab is to train the neural network. And this will take, on my machine takes about 100 seconds every time. And on your machine, it might vary depending on the capabilities of your machine. So it's possible you might not be able to complete this lab with your particular computer, but hopefully you can, and you'll see an opportunity to have your own computer train a neural network. So let's give that a try. All right, I'm going to move to our lab here now. So we're at our beginning Chem AISTRY Introductory Lab Sequence Part 1 launcher. And if you're just coming to this video from another direction, the first video in the playlist for this series shows how to install both this program and the data sets that we'll be needing for these labs, including this one. Once that's installed, then we just get it up and running, and we will run here now Cobber Crystal. So as with the previous lab, I haven't been able to figure out how to get the appropriate Python files that are associated with learning, machine learning in convolutional neural networks, to work without having this background Windows terminal. So that'll just have to run in the background. And as you saw, there's a whole bunch of nonsense that pops up and runs. Okay, so here's what it looks like. Now let's go to the lab and see what we should do during this lab. So what we're looking at here is that a whole bunch of lattices have been created, and they vary in missing atoms. So here's a missing atom right here, and then these, where the yellow arrows are pointing to, those are called edge atoms because there's a dangling bond here. They want to bond to this atom in this lattice position. Then what happens is these data, or these atom positions, show up in an actual crystallographic image as something that looks like this. And we're going to look at the whole thing. So what we're feeding the machine is a collection of crystallographic images. And so we're going to feed it both this big picture and then a blow up. So there'll be two images and then a information associated with those images, which includes the number of edge atoms. Okay, so then we're going to say that the number of edge atoms is related to the chemical activity of that surface, which is it's not unbelievable to think that would be the case. Now, there are traditional non-machine learning methods that have been used in crystallography associated with something called Fourier-transforms that allow one to process these data. So the question is, why do the machine learning? What's the point of it if we have these traditional methods? Well, it turns out for the very messy ones, the ones with a lot of surface defects, the Fourier-transform, the crystallographic data, is very complicated, and to back calculate out the lattice is very difficult and can lead to error. And it turns out that these machine learning methods are actually a little bit better at doing it. So let's compare two examples. So this one here is a blow up of a nearly pristine lattice. This is just one atom missing. And then this is a blow up of a lot of atoms missing. And you can see there's quite a difference in the structure. This looks a lot noisier. And yet the machine will be able to learn through these patterns, looking at these patterns. And again, we're not giving it numbers. We're just giving it these black and white, or grayscale, I guess, photos for it to study. Okay. Now, we're going to be trying different layers, number of layers, we're going to be trying some other parameters, which we'll talk about in just a bit, and we'll see how that affects things. So this leads to the question, why don't we just use hundreds of layers? Because if each layer gets a little bit better at marking off different features of the image, wouldn't it make sense to just use a lot of layers? Well, there's two main reasons why we wouldn't do that. One is, as you'll see, even with 2 layers and 3 layers and 4 layers, which is what we'll do today, the calculation takes a lot of time. And so there's a trade-off with computational time and accuracy that one would always be considering. And second, there's this really important idea of overfitting. And I've been talking about this throughout this whole series, and here we'll finally get to see actual overfitting happen. And what overfitting is when the model is trained so well on one particular set, it learns the features that aren't even physical there. It learns the particular noise that came with those data that aren't really a physical thing. And so when it comes to then seeing a brand new set, it doesn't match, it doesn't predict what things should look like quite as well. And you actually get worse results, larger mean absolute error, than you would get if it wasn't trained as much. So there's really kind of a sweet spot that a chemist would be looking for to try to best train his or her data to perform with the least amount of error. So it's not just more is better. Okay, let's look at the number of parameters we're gonna explore. So we're gonna look at numbers of layers, and we're gonna use 2, 3, or 4 layers. So we're gonna try with 2, 3, and 4. Now I'm not gonna go through every one of these, but you will go through these in the lab, and you'll compare the results with 2, 3, and 4. And what you will see is that 3 layers actually works better than 2 or 4. And that's precisely this example of overfitting. We will just use a very common number of filters. So I talked about each filter is picking out a different feature of the image. And so we're going to use 32 filters in the first layer, 64 filters in the second layer. So you always tend to, or a good working rule of thumb is to increase the number of filters, and it's common to use powers of 2. So 32 filters, 64 filters. For those that have 3 layers, so we're going to look at some with 3 layers, that we would use 128 filters, and then for 4 layers, 256 filters. Now, it seems like the time might explode on this, but it turns out all of these take about the same amount of time to calculate. And then something we won't talk about much, and that is the number of epochs, and that's just the number of complete passes through the training set. We will, though, look at and compare doing that with 10, 15, and 20 epochs. So the more we pass through that same data set, the more we overfit the data. And we will see that, that there's actually a sweet spot here, too. Okay. So we've got the program open. As we look at this, hopefully by the time you're looking at this, we'll have a revised version of the manual. But the first 2 steps here are obsolete because we have the actual launcher program. So you don't need to go and find the individual programs. So we just use the Cobra Crystal program off the launcher. And so we're really going to start here with set 3, or with number 3. So we're going to load a data set. So we'll select the data set. And my data sets are here with Cobra Crystal. And so you're just going to select that, and we're going to actually select the whole folder. So inside this folder is a CSV file with the metadata. So that has image number, and then the number of edge atoms and some other parameters as well. And then it has a subfolder, FT images. We want to select on this outer folder. So get all the way to Cobra Crystal, and then say select folder. You won't see any files here, but just select folder, because you won't see the files that are sitting in there. Now, it takes a little while for this to load, so this could take some time on your machine. It's loading all of the images so that they're in RAM, and then it'll tack it with these training runs. So I think we'll be okay here. I'll just stay on recording because I don't think it'll take too long to actually load the data. And then we will start our first run with 2 layers and 10 epochs. And that'll give you a sense of how this goes and what you should look for. Then I think I'll probably close it there and let you just complete the lab with the different types of runs. Okay, so it says it's successfully loaded. So now we will run the model. And so I'll run the model. We'll look down here. You can follow the progress down here in this bottom bar. So we should see a little green patch start here. It'll update about every 10% of the way done. So here we're 10% of the way done. I'm going to pause the video now. I'll try to start it up when we're about 90% done, and we can watch it finish off. Okay, we're back. It's about 90% done. And so we'll let it finish off here, and then the data will pop up. And so what do we see here? Well, this is with a 2-layer model, 10 epochs. Information is being put down here. So we have the configuration of the model, we have the training time, and then we have the mean absolute error. So you're going to fill in this. We'll maybe do one more here, but you'll fill in the rest of these as we progress through the different model configurations, and you'll look at how things look. So we can see here there's kind of a swoop to this. Does a pretty good job down here at low site defects, but as the defects get more, it gets worse. And we would anticipate that as well, but this is more than probably would be acceptable. So let's go ahead and try to run a different one. And my computer's been flaky here, so hopefully it doesn't crash. If there's a big cut in the video, then that's what happened. But let's try it here now. So we'll go 3 layers and 10 epochs. So what I'd like you to do actually, let's go 3 layers, 10 epochs. So 2 layers we did, 3 layers, and then go and do the 4-layer 10 epoch, and then come back and do the 3-layer 15 and the 3-layer 20, and then compare those numbers. And you should see this idea of overfitting in both of these cases. So let's go ahead and run the 3-layer 10 epoch. So this would be a direct comparison, just one additional layer. And so let's see if we get a little bit better value here. So I'm going to go ahead and run the model. And so I think this will refresh here to 10%. Yep, 10%. So I'm going to pause the video and pick it up again when we're almost done. We're about 90% complete. So we'll let this complete. And there we go. A little bit better. So we got just slightly better here. And so there it is. I guess I'll run through this so that we can kind of see. I'll do the 4-layer 10 epoch now too. And so there we are with 6.69, slightly better, and actually a little bit better training time. So that's interesting. I'm not quite sure why that is the case. So let's try 4 epochs. We'll run the model again. Down to 10%. I will pause the video. And there we did 4 layers. We see quite a bit worse. So and we can see this visually as well. So an overfitting situation here. 2 layers, 3 layers is better, 4 layers is worse. So optimal 3 layers. Let's go ahead and run the 15 epoch. I'll run this pause and we'll come back. Probably just come back. I'll come back when it's all the way done. Okay, we're back. I actually ran the 15 layer and the 20, or the 15 epoch and the 20 epoch, and I think I misspoke. I definitely misspoke earlier. Well, not misspoke. I misremembered. We actually are getting an in. So we look at this one. Here's the 10 layer, then here's 15 and 20. So we're actually getting better as we go down. I was remembering that as hitting the sweet spot at 15, but apparently we can continue to get better with more passes through the data. And this really scales linearly pretty much, just about. So the 10 layers took 91 seconds. The 20 layers took about 180 seconds. So about double that. And so you double the number of times through, it doubles the training time, which isn't too bad. It's not like it's squaring the training time. Okay, so we've seen now here in this lab, our computer was actually doing the training on these data and getting characterization of the results of those trainings. And so why don't you write up a conclusion, kind of maybe practice this a little bit more and get a good sense of what's going on here. And here are some kind of reflection questions to think about to help you do that. And this ends then the first part of the Machine Learning for General Chemistry series. And we will be having a second part that deals with some other aspects of machine learning, including unsupervised learning and different types of reinforcement learning. So there's a lot more to machine learning than what we've done, but you've now started to learn some of the vocabulary and some of the ways to characterize the different models. So hopefully you got something out of this and can take these ideas as you move forward in your chemistry education.